take off the recording pause. Okay, good morning, everybody. Welcome to the OCP HPC sub-project meeting. Let me just share the basic screen. Hopefully you can all see that.
You can see it.
Great. All right. Okay, so welcome to this week's meeting. I'm actually broadcasting from Sweden today, so I'm not quite as prepared as I normally am. I did, just from an OCP perspective, I did make a visit up to Luleå, to the Research Institute of Sweden, and met up with John Summers and Chate. They do a lot of thermal research work from thermal management. And so that was good to get up to speed with what they're up to. And we talked about potential collaborations on some of our thermal concepts that we've talked about in the past on the HPCM. I also had they kindly took me to a data center there, saw some OCP equipment and also some NVIDIA equipment as well, some H100s actually in operation, and learned a little bit about the data center infrastructure up there. Really pretty impressive. Anyway, so but I'm also here on for other reasons as well. So yeah, so in terms of general progress, for those of you that weren't on the last call a couple of weeks ago, we were talking about the Open Systems for AI initiative, and the fact that we're looking at how do we move forward with accelerators, and I guess the general tone was integrating that into potentially into the DCMHS under an umbrella of that, whereas traditionally the OCP accelerator infrastructure has been the sort of a separate side work group on accelerators. So and obviously taking some input from where we've seen NVIDIA take it with their Blackwell platforms. But so today I wanted to make a little bit of a more detailed discussion on the interconnect of this bring up concept that we're talking about. So again, for those of you that weren't on the call, I can touch on it again briefly, but we'll be talking about we have a bring up process that every silicon startup certainly goes through. When a new chip comes from a fab, they have a bring up board, and they have a socketed situation to plug the new chips into and just get them basically up and running, and some basic verification before they get soldered onto the same boards and then handed out to engineering, software and firmware engineering to test the chips out more rigorously. And then those boards are typically used as reference designs to pass on to ODMs that are maybe going to design specific modules, like the OEM module, for example. But the idea was, would it be possible to make the bring up platform an early deployable platform? And so that's something we've been looking at. And then maybe you move forward to the full-on, in our case, the HPCM, the module that we've been working on under this work group for the last 3 years or so. So, and I'll basically just touch on that a little bit today. Just in terms of, I don't think Bijan is on today's call, but just in terms of some discussions with him and the directions that we can potentially propose that we could put forward as a group to the Open Systems for AI strategic initiative discussion. So But as we normally do, let's go for our introduction of new attendees. So we have a couple of new attendees at the moment. So no particular order. Mark Cram of Legrand, would you like to give a brief introduction of what is it who you are, your company, and your interest in what we're up to? Would be good.
Okay, very good. I'm Mark Cram. I'm Director of New Market Development for Legrand in their Data, Power, and Control division. I'm based in North America. And I've got a power background, a chip background, and also a systems background, having come out of PCs Limited or Dell way back in the day. So just trying to scope out what the nature of the project is here on this sub team and figure out what Legrand's participation should be or could be in that effort.
Okay, so you're a power specialist company.
At present, yes, we are a power specialist company. Amongst other brands, we've got Raritan Server Technology and Starline Overhead Powered Busway. We make a number of data center cabinet brands amongst them. We have done custom racks and cabinets. We've done networking hardware. We have fiber optic components. We've got a number of different things in our portfolio.
Okay, interesting. All right, well, welcome aboard. And the next was Masood Zaran.
Hey, good morning, everybody. So I'm a recent hire towards AMD. My background's been mostly in HPC environments and genomics, national lab, and I am now part of a system network GPU performance group and pretty much working on a lot of the newer devices that AMD is going to be rolling out and testing out different, I guess, versions for manufacturers. And I'm just trying to kind of be a fly on the wall and see how well this subgroup fits.
Okay. Sounds very good. So thanks very much for joining. So how do you pronounce your name? Is it Masood Zaran?
Yes.
Okay, thanks. Welcome aboard.
Thank you.
Okay, so yeah, well, maybe for you two in particular, if you do go onto the wiki, in fact, I'll just share the wiki page. There, in terms of the what we've been doing is our core focus over the last actually 3 years of concept building. We've never really had any funding to go beyond concepts, but we have had lots of participation in refinement of our concepts over the years. But this welcome section is a pretty good way for you to get up to speed. So it's in the particular order. It's we actually did put forward a proposal into the New Frontiers funding program at Oak Ridge National Labs, DOE, which we are still awaiting to see if we're going to get funded or not. So that's an actual written paper that would give you a background if you prefer to read some papers. You'll get some context there. But back in OCP Global Summit, just a minute. Yeah, so this is in a sort of reverse order, I think. Or maybe the order is I'm just looking at I could do the reordering this. So this, but there's 2 years worth of OCP Global Summit presentations. They give you a generic overview and sort of very specific overviews. So the 2023 presentation, October 23, was really where we gave the first intro to the HPCM module, and then there was a regional summit in 2024 where we actually went into some specific details on the power, thermal, and universal interconnect. So you've got the recordings and the slides on both of those. And then we talked about a specific application of building a digital twin ASIC emulation platform using our HPCM wall of compute. And that was in this year's 2024. in that way, that was what we used to for our proposal into the DOE New Frontiers funding. So that gives you a little bit of an overview from of a particular application with that product. So on each of these presentations, I tried to give a little bit of an overview for the audience that it was brand new to it, but that 2023 one gives you the a broad overview. So anyway, so that's for anyone new, that's a good way to get up to speed if we seem to be jumping into the middle of things here. Okay, so what I wanted to do is if I switch back to our presentation from the last meeting, we were talking about this Bring Up platform, and we were talking about the migration that we're seeing. We're talking basically the Open Systems for AI initiative is looking at bringing the DCMHS and OCP OAI chassis together in what we're calling Open 72. And taking inspiration from what NVIDIA have done from their DGX HGX towards the NVIDIA Link NVL72 rack scale computing. What we were talking about is we were talking about this Bring Up board as maybe a nice concept that we could bring into making deployable Bring Up products that could be integrated into DCMHS and actually have a process that we were talking about here. And these pictures here were the basic idea of having a cabled module where we could cable things together inside the DCMHS chassis. And for those of you that remember, we were having the interconnect being brought out underneath the cabled I/O so that the tops would be clear for thermal management, either be it water cooled or hybrid water and air, or an air cooled solution. So we went through some pictures of that where we had, this is showing 4 modules cabled up with these HPM, the CPU boards that are part of the DCMHS standard. We started in a 19-inch rack. In my efforts, we are we're probably going to switch over to the 21-inch rack as a preferred solution, but I did want to try and squeeze this into a 19-inch, so it was an option. And this picture here was showing we went through the potential cabling of a particular given topology and how that would look. So I've had a little bit of discussion with Amphenol and Lotz on this in terms of how we do these interconnect, which is what I wanted to get into today. So on that, so let me just grab a couple of pictures here. So here's our latest update. So we started to integrate in some of the water pipes coming in, and if this is like a water cooled example, can we get all this and fit it into a 1U box? We've got the cables underneath, so we're trying to put some infrastructure into the chassis. And again, this is cartoon stuff. I'm not a mechanical engineer, so this is just cartoon stuff that maybe we can get mechanical engineers to at least have a starting point as to what our thinking is like. And what did I want to show? This one here is maybe a good one. So this is the back side of the modules. And the key thing here is these connectors. As you can see, we've got a frame here, and this frame needs a little bit of modification still. It's not the finished article, but this was going to give stiffness to the board. It was also going to hold these connectors in place mechanically, which I'll get into in a moment. And also, if we did have vertical power delivery, this could provide a little bit of a heat sink cooling for cooling the vertical power regulators on the back of the board. You could get airflow across them. So that's where we've got with the concept, and I'm starting to talk with full-on engineers in terms of getting this modeled up properly. So diving into the connectors, let me just bring the model up itself. So here is the model, as we can see, with this frame on. So if I just take the frame off a moment, what we've got here is working with Z and Lotz and Amphenol and Lotz. We wanted to get rid of all of the through-hole features of the connectors. And so obviously that takes mechanical strength away from these connectors, so they could easily be torn off of the board. So we need to replace those through holes. So the idea here is getting rid of the through holes prevents clashing with components on the other side, and also improves routability without holes being all over the board. So what we've done is, this is a standard MCIO connector, but we've actually taken the metal shell off of it, which also had the through hole features in the metal shell. So this is just the plastic bodies, and they also had plastic alignment pips that were needed for going through the board, and we've got rid of those as well. So these are full surface mount. So I wanted to just start asking a few questions of our connector experts on the call in terms of what we're doing here. So firstly, that's the idea. We would pick and place these connectors as we see, and they would get now the first problem that comes up is their alignment. Without the alignment pips, what is our probability of getting a good alignment? And I guess while we're on that part, let's just cover that now. So I know that basically when you've got the pad outlines and you have the solder paste on the boards, you'll get a capillary attraction where the pins line up with the pads. But to a certain extent, you're going to need a very accurate pad specification, I'm assuming, if you're going to get a very precise alignment. And my other question really is, can you even rely on a capillary attraction, maybe especially on these bigger connectors, or not, in terms of the precise placement? So I guess Z or the Lotz guys, is there anything you can comment on there with regards to physical alignment or the pick and place or the initial mechanical pick and place alignment of these connectors if the pips were removed?
Yeah, Alan. So I think the principle is there, right? It's like we see the how chip is being soldered, and they depend on the solder paste when it melts, its surface tension to align the chip to the board. So I think the principle this could work. The only thing is the footprint on the connector like this, it's not symmetrical. It's not at the center, right? So
the connector, right?
Yeah, the connector footprint, especially the right angle one, is the footprint on one side, and the weight of the part, the center of the weight of the connector, actually is offset from the footprint, right?
Right.
So we are not exactly sure how will it work, right? I assume there will be a misalignment when you place the parts, and you need to depend on the surface, solid surface tension to rotate to be perfectly aligned, right? So, so I think I only can say that we don't have that experience yet. The principle we think it may work, but how much the surface tension, the force surface tension can provide, and how much the friction force, right? The parts on the board that may, that's out of our kind of current knowledge. If the surface tension is strong enough, certainly it will rotate the parts to the right position. So,
Okay.
There are other applications where there is a solder down foot, but it would mean, though we're removing the shell, which normally provides that strength, we would have to add a shell back in that would provide some strength as well as alignment for the leading edge. Now, because as Z said about the offset solder tabs, the leverage that's available as you mate and unmate the mating cable would generate some leverage as well that I'm concerned about
Yeah, right.
damaging either the joint or stretching out the,
Yes.
deforming the contacts.
Yeah, so the mechanical side, I think I've got covered, which I wanted to get onto, but it was the alignment of these aligning in the correct way. Now, the way I used to work with a connector company, well, Molex eventually, but a smaller one that Molex acquired. And so when we had a couple of projects where we had multiple connectors that we wanted to be aligned, and we would build a jig that would hold the connectors as you put them through the reflow, and you'd place them as one large component, and then you would have alignment features. You would use the holes that were other holes that are in the board, like these other holes that you see, and so therefore you would get a more precise alignment, and certainly the connectors relative to each other alignment by that jig. So it'd be like a plastic jig that would unclip after they were soldered in place. Are you familiar with that approach when you're putting multiple connectors down, and have you guys ever done that?
I think that's somewhat common, that there's a frame, but the nature of the pick and place process is incredibly accurate, and the vision systems that's used for lining things up does a great job. But if you look at this connector, there's airspace underneath, and so there is an opportunity for the connector to tilt. Oh, there's some feet on these.
Yeah, you got some feet on this.
Yeah.
Okay, so and this is just the plastic bodies, by the way, at the moment.
Yeah.
So all right, so I mean, I guess the general feeling is either we will be okay with alignment with the pick and place itself or the capillary attraction, but a jig is not necessarily a bad way to go as well. If we want to build a frame where these connectors would be previously they would be picked in place as one big unit, and then they got their alignment with these other holes.
Yeah, I just am still concerned about the leverage.
Yeah. So okay, that's
because there's going to be a pretty tight radius coming off of these parts.
Yeah.
You're expecting to plug them and then make a sharp turn.
Yeah, so that's where the frame comes in. So what we've done is we've taken off the metal shrouds in the through hole legs, and what we do is we replace it with this overall frame. So hang on a minute. Move. Stop. It's frozen now. There we go. Thank you. So you can see here that basically at the back, this frame would be such that it it would mate and you'd get a friction grip at least with this frame and the connectors replacing the previous bodies that were there. So that would be the idea. And even the latching holes, if you had the same cable latching holes, that would be built into the frame, so you'd still be able to clip the cable into place. So in terms of turning this on, I can just switch to one of the pictures. So here you go. Here's a close-up of a cable plugged in with the frame, and you can see it keying in. So basically, this entire frame provides stiffening for the board, holds the connectors in place, and additionally, it also provides the potential if we've got power devices, vertical power, then this can provide a heat sinking as well to the vertical power devices on the back of the board. So this has got three purposes as well as being stiffener. Now ignore these very high edges. These are going to be dropped around here, so the cable can more easily exit. So does that allay your fears, Howard? Does that make sense, or am I missing?
Yeah, that's better.
Okay, good. All right, so that's that side of things. So it did. So if I'm hearing right, please correct me if I'm being taken too optimistic a view. We don't see this as an insurmountable approach to these connectors. Is that fair to say?
Yeah.
Okay, good. And Z, are you happy as well?
Yeah, I think I agree with the principle here. So yeah.
Okay, great. All right, so that covers the basic connectors. Now, the other discussion we had a little bit offline was the cable bend radius. Now in this particular one, I don't think we have the cables, so I don't have it in the model. Let me just see if I can let's go back to our presentation here. So there's a couple of things that we just zoom in here. This is a view from the top. So we've got our cables plugged in. There's a couple of areas. Now look at what we've done here. But we've got a cable just going this very short distance between two modules. And I do know, or when I was at Molex, I do remember that there was a certain length. You couldn't make them very short. You couldn't make them just as short as that gap. So there's a minimum length of the cable. So what we've shown here is like a freeway fold. So the cable ejects out, it bends downwards, it folds around, it folds back, and then plugs into the other one. So I'm not sure what the total length of this, but do you have a minimum length of cable on an MCIO cable that could be built? And it's just a manufacturing process that limits the shortest length.
Alan, are you adhering to bolts? We have tried 150 millimeters.
Sorry, you have tried what? Sorry?
150 millimeters for
100.
the MCR. So that's about 6 inches, I think. About 6 inches.
And you say you've tried it. Does it work in volume or not?
It's a prototype build only.
It's prototype only, 150 millimeters.
Yeah, for assay testing. Yeah.
Right. And Z, is that a length that you can cope with, or can you do shorter, or?
Yeah, that sound I think right length for me, and I think maybe there's two things, right? When it goes shorter, one thing is the assembly issue, right? It's how short the assembly can take. I mean the manufacture assembly process, right?
Yes, that's
yeah,
right.
yeah. So that is one limitation, and the another one is SI when it goes shorter, and apparently the return loss is getting worse, right? So so I think I've been seeing kind of this kind of number as well, but let me check whether this is the shortest for the assembly line. I think one thing I want to ask is if okay, it's too short, if we can use some kind of smaller wire gauge, right, to actually increase the insertion loss.
Oh, no, that's a good idea. Or we could even do a little flexi if you could make a flexi of the connector.
Yeah, so it's kind of a little bit of compensation there, right? So therefore maybe we can do the shorter distance, just limited by the manufacture process, not by the SI. So
yeah, no, I realize that. Yeah, I knew it was the manufacturer. Yeah, and I have heard the shorter the cable, you've got the discontinuities and the reflections, or everything comes back stronger, so it causes them more problems, right? So, and I'm not sure if they can. Yeah, I'm not sure how much work is done on the silicon side where you can limit the transmit power at all. You know, back off the transmit power as well as always need this additional loss. But okay. But I think that's a good idea. If you've got a little bit more lossy material, or we could, I'm not sure if you can make a flexi with these connectors. I guess we can, couldn't we? Because they're paddle cards, so you could actually build literally a flexi with the paddle card itself at both ends for shorter distances, and you could increase your losses quite easily with a flexi.
yeah, so I think my thinking is I may check with our team, see whether there's possible to even go down. And
Yeah.
Yeah.
Yeah, Z, in one of our test build, we have attempted to go as short as 120 millimeters, but there we have seen a much bigger risk on the return loss. And I think that's the limit of the assembly fixture that our team has or can do, or basically it's a process limitation for that length. That I'm
Yeah.
not sure how much or how long your team can do, but yeah, it would be nice to know.
Yeah, so I need to check with our team. So I think the thing is we are thinking out of box here, right, for this project. So
yeah,
and
Would you guys do flexi cables for short distance?
yeah, that the thing is with the flex cable is I mean the flex PCB, right? Basically, it's flex circuit. Their loss is high.
Right.
So usually we don't use it, but yeah, for this this is very short.
Yeah, I mean, I think this
yeah,
is
maybe is a choice. Yeah.
Yeah, you need a little bit of flex in there. You need to put a bow in it, because to unplug and plug the connect the cables in. But that might be a nice option. And it gives you the additional loss, plus it's short enough. So, all right, okay.
Yeah, but I think maybe when we walk away from this topic, can I ask what's the targeted speed we are talking about?
Well, on this, we're at MCIO speed, so I mean, what we're looking at in this particular one is PCI Gen 6 speed, so 64 gig. But obviously, I guess as we move forward, everybody wants to get up to the 224, obviously. But I'm wondering if we would move to different connectors if we were trying to do 224. So there are other ideas that I've had. Looking at the different types of cabled connectors that you guys all do, But I wanted to keep it in MCIO for now, because that was what we've been working on with the Universal Topology Interconnect discussions on HPCM, and that is the PCI one and CXL one as well. So, and that's what these motherboards, these CPU boards also use the MCIO for their PCI connections to the accelerators as well. So I thought let's do it with MCIO for now, and if we can make this work, then it's a good start. I don't think if we do end up being able to make this an OCP standard, or we contribute it to OCP, we'll only really be contributing the board size and the mechanical holes and the how you get the power delivery, and certainly host cabling might be specified, so you can cable into a host connection, but the cables between the modules, if they're a different sort of standard, I mean, they could be a different cable approach as well. So that's where the OCP compliance could vary, if people wanted that too. But yeah, ultimately, along the lines of our universal topology interconnect, we said we would like this to go all the way to 224, right? So yeah. So, but that would then be a question as to whether MCIO is ever going to get us to 224 or not.
Yeah. Okay. Yeah, I think for short term, so basically saying we can start with the PCI Gen 6 cable.
Yeah, I think that's a great start.
Yeah. Okay.
Now the other thing that we did discuss was so if we look on, let me just bring up some of the.
Adam, maybe I think I ask this question. So what's right now? What's the gap between your two modules?
The gap here.
Yeah.
I think the gap here is of the order of
2 inches.
Yeah, maybe up to 2 inches. It's like between 30 and 50 millimeters. I'd have to go back and measure it.
Okay. So you are actually looking at the much short cable, right? 2 inches is 50 millimeter.
Yeah, if you look here, we've got 3 folds. So that if this was 50, that would be 150. But if it's 30, I think it might be 30 actually. Then we're looking at about 100 millimeters of cable here with a triple fold, or a double.
I see. Okay.
But if we could do a flexi that was just around about 50, then that would be a great solution there. Now on the others, let's see if we can get a diagram of this, and if not, no, let me just bring up one of this one here. So here, you can see that we're basically going through 90-degree folds. So I remember in our email conversation, basically what we did on this was we assumed that the flat cables where you've got 2 twin axes sort of sitting on top of each other, if I understand correctly, then we assumed that the thickness of the cable would be about 2 millimeters, and we assumed an internal bend radius of 2 millimeters. And so basically a completely folded cable from top to bottom would be 6 millimeters, if I get that right. But I think Z, you were saying we should have a 3 millimeter internal radius if we wanted to get up to the higher speeds. Was that right?
Yeah, that was when I'm thinking, if we go higher speed and long reach, right? So you actually have a very short cable, and now I'm wondering what's the longest cable, right? So when you get like half-meter cable length, then getting to the to the higher speed, like 224, I believe we need to go a little bit thick on the conductor. So
Right.
cable size will be grow, and then certainly the radius. That's why I kind of reserve a little bit space for that. That's say the radius will be 3 millimeter.
Right, right. So what about the thickness of the of two cables sat on, you know, of one of the flat piece coming off of the cables? What's the thickness of that?
Yeah, that is about 1.1 to maybe 1.2 millimeter.
For two diff pairs sat on top of each other?
Oh, you mean the two cables stack
Yeah,
up?
so yeah, obviously here you're going to have two cables because you've got two rows of pins, haven't you? So you'd have two twin
Yeah,
axes
though
on top of each other.
actually two rows. Let me think about it. Yeah, actually two rows. It's one cable.
Oh, is it?
Could you correct me?
Oh, right. Okay,
If
interesting.
yeah,
Yeah, that's about one cable C, two
yeah.
rows.
So we're at 1.1. So in fact, we're not too bad here because I think this model has got 2 millimeters for the cable thickness and 2 millimeters for the fold, internal radius for the fold, and then 2 millimeters for the top piece. So this is a total of 6 millimeters. So if you're saying it's 1.1 and 1.1, then we've got 3.8 of bend radius available. The bottom line here is we are layering a few of these maybe on top of each other. Maybe they're not on top during the fold, but where I've really concluded is we probably need about 10 millimeters from the base of the board to the bottom of the chassis is what we're going to need. And here, by the way, this is the bottom of the chassis. You can see that we've got windows in, so you can actually plug these cables in from beneath. So this is where a bit of mechanic. I don't think we need this T-bar here. That can be open. But so this is where some refinement needs to be done on the mechanical engineering side. But the idea was if we keep this, and another thing I was thinking of is if we think of an OAM module, you know, typically an OAM module is going to have a motherboard underneath it that we don't. And I think the OAM module, the mezzanine connector, the underneath of the OAM module to the top of the motherboard is like 5 millimeters. Then I think the motherboard's of the order of 3 millimeters thick. And then there's I think there's a protection plate under that. So you're probably in the region of 10 millimeters from the base of a OAM module to the chassis bottom. So I was thinking if we can keep in that 10 millimeters under the board, then we'd be in pretty good shape with all the cables, if that makes sense.
So I have another thought actually. Certainly, yeah, I think you have the limitation of the bottom space, right? So that's why you try to use the right angle connector.
Yes.
But the whole trend, the whole industry trend right now is going with the vertical connector.
Yes.
The SI on the right angle is very challenging. And
Yeah.
the vertical connector, actually the mating height get lower and lower. So it's kind of like the right angle, it's lose the attraction. So if I'm trying to think if you can reserve like maybe 11 millimeter, then maybe you can use the vertical connect instead of the right angle.
Okay. But vertical on the bottom of the boards.
Yeah, vertical and the right angle plug. So it's a vertical receptacle, but with very short, right? The right angle cable.
Right. Okay.
And it helps your assembly motion as well, right? Like this, you have to insert the cable from the side, and you need to leave some space on the side. But vertical wise, you just vertically plug in, right? So you don't need to leave the space on the side.
And then, and this 11mm high connector, is this still MCIO?
Yes, yes, yeah.
Okay. All right, that's interesting. Okay, I didn't think of when we were talking vertical, I was assuming we'd have to be on the top. So that's you think 11mm will be enough? Can you send me the latest models with that then, Z?
Yeah, I can. Yeah, I will check. Yeah, our team to get the model. Yeah, you can try it. Yeah, and
okay, that because then our mechanical clamp would just clamp down on the edges of the connector to mechanically hold it. So that would be easy. That would be straightforward. Okay, okay, that might work. All right. I'll take a look at that then. Yeah, interesting.
yeah, so I think that will help on the SI side. So if we want to go higher speed, so like PCI Gen 7 or 224.
Right, right. Okay. All right. So okay, I'll take an action to explore the vertical. Yeah. All right. Okay. So I think that's everything on the interconnect. That's gone about as well as I could have expected. The and the vertical ones, okay, a possibility. I guess what we need to do to really get to that, though, you know, my honest opinion here is when we come to the adding the it's what the height of this board will be and whether we can get the heat sinks on and still stay in a 1U chassis. That's the I think that's a burning question. Is if we need 11mm on the back of this and a 45mm 1U rack, can we still get the these water cooled heat sinks on? So that would be the question.
Hey, Alan, I think Z asked this question, but I'm not sure you answer. What is the longest cable you need?
The longest cable is probably coming from the host end here. So from one of these fire modules, the by 16 cable would connect to the host. So it would come out, it would come up here, and then it would plug into the MCIOs on the HPM of the host board. Now, I'm assuming these MCIO connectors would be at this end of the board, but that depends on the vendor of the CPU HPM board, and they could be at this end. So that might make it longer. Like this board here, I believe is 305mm long. And I think the total chassis length is of the order of 800. So the absolute maximum cable length would be 800, but I would say you're probably more like half a meter maximum.
Okay.
Is that good? Bad.
Oh, it's an estimate right now, right? There's something that we don't know, so.
Right. Yeah, no, I would say half a meter, and most of them, like the interconnect between these modules we're going to be talking is probably going to be in the 300 or less range. Millimeters. Okay. All right, we've just got 5 minutes left, but I don't have a lot to talk about on the HPCM, but I did want to start kicking it off. I didn't get a chance to make any upgrades to the models, but I have been speaking to Bijan, and I've been trying desperately. I don't know if any of you guys have got a 21-inch OCP rack chassis model that you could throw my way, but it would appear that no one has contributed a 21-inch DCMHS rack to the 3D model anyway, to the consortium. So I'm struggling to get a 21-inch rack at the moment. But here, let me just put it in display mode. Sorry. So this is, again, for people that don't know, this is the OCP HPCM module that we're looking at here. I can't show my mouse, but in the left-hand side of the pictures at the top, that's a module side on a single HPCM module plugged into what we call our wall of compute. So the gray box at the bottom is the wall, and the module is at the top, and it plugs in and it collects water. A blind make water directly to the module, and blind makes the power as well, 48-volt power from the wall. The wall has facility power going down it as well. So there's a power supply in that wall. For every module, there's a local power unit that converts the facility power to the 48 volts. So you've got a very, very short path from facility power to the point of load. Again, if you look at the NVL72 system, they have got up to 2.5 meters between facility power and their point of loads, which there's a lot of opportunity for loss feeding their modules. So this is one of the benefits of our approach. So we've always been talking about the wall of compute, where we put these modules in a wall. There is no 19-inch rack, but the idea here is that we actually fold these modules into mini walls that slide into a standard chassis. And the size of these modules right now is such that we can get about 3 of them vertically, and probably enough room to get some cabling out the back of the chassis. So that's good. I was hoping we would get 4, but that would be completely jammed in, and I don't think we can make the modules much shorter to fit 4 of them in. But if we go to 21-inch, this is a 19-inch chassis, and we're showing 9 modules, 3 by 3. But if we go to the 21-inch, we would be able to easily squeeze in another module and make it 4 by 3. So we'd get 12 modules into the rack, into the chassis. We would have to be 2U, and this is where we would need to shrink. So the wall we'd actually make the base of the chassis. The chassis itself would be like a laid down wall. So, but we would make the wall thinner than what we've shown in this concept. And obviously there's only going to be 3 modules per wall length, and but 4 columns of them. And so we're working on, can we crunch this down? And this does use these vertical cables. So actually the vertical connectors. So actually if we were that purple cable in the middle there, we were trying to experiment with how high that was going to be. So you've given me a good answer there. I think we've got a lot higher profile on what we've done here than what we may be able to achieve. So that's great news. So that's great news in terms of our ability to, because at the moment, if you look at the dimension of the module and the wall as it stands right now, and we think we can thin the wall down quite a bit, we're at 90 millimeters, which is exactly a 2U thickness. But the height of the copper at the top, the manifold, I believe that's a lot higher than 11 millimeters. That's of the order of 25 millimeters, I think. that manifold. So if we can eject cables at 11 millimeters, we would be in pretty good shape to stay in a 2U chassis with this. Now, the key things that go on here, and I was reading the Open Systems for AI white paper, they're talking about racks going up to 250 kilowatts, 500 kilowatts, and up to 1 megawatt per rack. And so we would definitely need, in my mind, this drawer, if we had 12 of these in here and they were like 2 kilowatts each per module, let's say, you've got roughly 24 kilowatts here, you know, or 1.5 to 2 kilowatts. And if we actually were plugging in the SSDs, you'd be in a 4U space. But that would then take you up to, you see your power density would go down, but that would add extra load. So that was where maybe we'd go in excess, go more towards 3 kilowatts per module. But if we just assume 2 for round numbers right now, then it's 24 kilowatts per 2U. And then a 42, that's 21. So you fit 21 of those in. So for round numbers, 20 times 20 is, yeah, you'd need a 500 kilowatt chassis to power this. And that was where Bijan was going, I think. So fitting 12 of these into the 21-inch wide chassis is what we're going to do next. And we're gonna optimize this, but with Z's input on the height profile of the MCIO connectors, I think that we're going to be in great shape there. So we're going to update the model for that, and then that was what we were going to take forward to the Open Systems for AI work group. So that's really what I was doing there. Okay, so that was really all I wanted to give you an update on, is of that we are. I am still making progress there, and hopefully we're trying to get the attention of everybody. So, Mohammed, if everyone's still on. I know we've run over a little bit.
Alan, excuse me, one question on the cable here.
Yep.
Yeah, is this open to another configuration to possibly reduce the height or the bending? There is
say that again. What open for configuration?
Yeah, the cable configuration that you have in the model is it's like a straight plug, right? Similar to the one that you have in the other slide. Because there is another version of the MCIO plug, which is what they call a side exit. It's like a flag style connector.
Yeah. So the cable actually exit to the right. That's what you're saying, right?
Yeah, right or left, yes.
Yeah, no, that was what Z was saying, I guess, for the 11 millimeters, right?
It's I believe Z is referring to a traditional vertical right angle that would reduce the Z height of the mated connector. What I'm talking about is another version. It's also a right angle, but it's like a flag.
Oh, right. Is this an MCIO version, or is this a completely different connector?
It's an MCIO version also. Yeah.
Oh, right. Okay. Well, if you can share some data on that would be.
Yeah, I'll work with Howard and let him share it with you.
Okay, yeah, no, if you can send 3D models of the PCB connector and the cable, that would be great.
All right, will do.
All right, thanks.
All right, you're welcome.
Okay, we've overran by 5, so apologies everybody, but I don't have anything else unless there's any burning questions.
Okay.
Okay.
Good presentation. Thanks for leading us through.
Okay. Bye everybody.
All right, bye everyone.
Okay, bye-bye.